Alright, so the first question just says describe what the scatter plot reveals about the relationship between the relationship of traffic delays and the number of cars on the roads. And so we can see from this that average vehicles per day is our independent and our response are explanatory, and our response variable is hours of delay. And so I haven't written this out for you, but I will read to you what I have that I wrote down. Is there appears to be a moderately strong positive linear relationship. So I talked about strength, form, and direction. So I said moderately strong, positive and linear relationship. So our form is shape is linear, our strength and our direction. Positive is our direction and our strength is moderately strong. So moderately strong, positive linear relationship between the number of vehicles per day and the hours of delay in traffic. I also went on to say that as the number of vehicles increases, the hours of delay increases, which is just another way to say it's positive, that they're both increasing. That's pretty much all it's asking me about for number 11. It's not asking me to go into any specifics or anything. Number 12, suppose another data point, 200,000, 24,000. So roughly here, somewhere around in here. Suppose that data point was added to the plot. What effect, if any, will this new point have on the correlation between these two variables? So if right now, before I added that point and I had to estimate the line, I would say somewhere in here. Maybe a little more tilted upward, but that's about it. If you start adding in this point, it kind of spreads the points out even more, and so it's going to weaken the correlation. So the effect that it will have on the correlation is that the correlation will become weaker, and it will become closer to 0 because the points are more spread out. That's about it for that one. 13 is the regression equation for that same set of data. So they ask us for the slope of the regression line. The slope is the number that's in front of the coefficient in front of my, this is my y-intercept, the constant, but this is my x variable. So the number in front of my x is 0.07822, and x must be the vehicles per day. That means my y variable is the hours of delay. So, and we always know that that's over 1. And so that's my slope, 0.07822. You could just say the slope is that. But then it asks us to interpret the slope in context of the problem. So for every, this is not true. I've got this backwards. This is backwards, this is backwards. This is the number in front of x, so our x coordinate is vehicles per day, so that's what's going here. And then delay is the y. Whatever, this is x, so what we're predicting then is the y, and we're predicting the hours of delay. Sorry about that, I hope I didn't confuse you too much, but I'm getting tired, I guess. So as the vehicles per day increases, so as the number of vehicles increases by 1, the hours of delay increases by 0.07822. And you could still put hours, but we've already said the hours of delay, or the delay increases by 0.07822 hours. That's it for number 13. Okay, so 14 is the one I told you that we may not know. S normally stands for standard deviation. We're used to talking about lowercase s. So this is very similar to that. Standard deviation is usually the average distance away from the mean. Well, for this case, this is going to be the average distance away from the predicted values. And so the way that I've summarized this is that the hours of delay for the observed points was on average 3,899.57 hours away from the total hours of delay predicted by the equation. Sorry, so that's a little, we haven't talked about that. We can talk about that a little bit more tomorrow, but that's basically, it's just like standard deviation of anything else. It's the average distance away from the mean. It's basically the average distance away. What we actually saw was from the values of the predicted equation that it would have predicted. This is kind of like up in the air. Same scatter plot, but they've noted which ones are in California and which ones are in western states. So it says to comment on the relationship between the average number of vehicles per day and hours of delay per year, how that differs between the California intersections and the intersections in western states. The first thing I would say is if I were going to come up with a prediction line for just the California states, it's going to be a much steeper increase. That as the vehicles increases, the delay increases at a faster rate. Whereas if you did a prediction equation through the western states, it's not going to have as steep a slope. It's not going to increase quite as fast. Also, there's just on average more cars on the road in California than there are in the western states. And that's about it. You're just noting some of the observations that you see between them. Excuse me. This is a little bit different. Breeding habits of the common crossbill in different years finds that there is a linear relationship between the number of breeding pairs of crossbills and the abundance of the spruce cones. And then they've given us statistics on 8 years of measurements. And they've already told us that X is the average number of cones per tree and Y is equal to the number of breeding pairs of crossbills in a certain forest. So I already know what X is and I already know what Y is. We don't have to do that ourselves. The correlation between X and Y is 0.968, and they ask us to find the equation, and Y is the response variable. So the first thing I need to find is slope, and that formula is equal to R times S of Y over S of X. So it's just going to be 0.968 times standard deviation of Y, which is 15.1, over standard deviation of X, which is 16.2. So I ended up with a slope equal to 0.9022, I think. So my slope is 0.9022. And then I just go back to the same old equation, the prediction equation. But now I'm looking for the y-intercept. So I'm going to get the y-intercept by itself. So all I'm going to do is subtract out. So it's just going to be y hat minus ax is equal to the y-intercept. But we don't know what y hat and x are. So we're going to use y bar and x bar instead. And so this is where I'm just going to plug in the mean, 18 for y, minus the slope, which I now already know is 0.9022, times x bar, which they told me up here is 23.0. And that should give me the y-intercept, which I ended up with hang on a second. Okay, so this will give me the y-intercept, and the y-intercept I ended up with negative 2.751. So now that I have my slope and I have my y-intercept, I'm just going to go back to my regular old form of the equation, and it's going to be y hat is equal to 0.9022x minus 2.751. And actually, if you wanted to come down here and say the predicted number of crossbill pairs is equal to 0.9022 times the number of cones minus 2.75. Either one of those would be correct. So that's the actually number 16. For what percentage of the variation in numbers of breeding pairs of crossbills can be accounted for by this regression? That's the correlation coefficient. That's r squared. So all we're going to do is take 0.968 and square it. I don't know that I wrote this down. Oh yeah, it's 0.937. So the percentage is 93.7% of the variation in crossbill pairs can be accounted for by the equation between the number of cones and crossbill pairs. Number 18, based on these data, can we conclude that the abundance of spruce cones is responsible for or causes the number of breeding pairs? No. It must be an experiment to imply causation. And this was not. So it must be an experiment in order to imply causation, which is not. And that's it. We'll talk about these tomorrow.